Namaste children, how are you all? I hope you are fine. And today we are going to discuss a new chapter named as real numbers, the first chapter. So real numbers we have come across even from the beginning of our school days. So real numbers, so what we are going to study in this chapter, real numbers. So real numbers, we have studied some part of this real numbers and some topics we have covered already in the 9th standard. In 10th standard, we are going to discuss about two theorems or two lemmas or algorithms. One among them, it is Euclid's division lemma. Euclid's division lemma. The first one it is Euclid's division lemma. Division lemma, or it is an algorithm. Division lemma, or it is an algorithm. Euclid's division lemma or algorithm. The other topic it is fundamental theorem of arithmetic. Fundamental theorem of arithmetic. Then the third one it is revisiting of irrational numbers. Revisiting of irrational number, that is proving irrationality of numbers. Proving irrationality of numbers. The last topic it is revisiting of rational numbers and their decimal expansion. Decimal expansion is whether the decimal is a terminating decimal or non-terminating decimal. Terminating decimal or non-terminating decimal. So those topics will study in this chapter real numbers. Now what is Euclid's division lemma? We have already come across this division lemma with the other name, that is division formula in the arithmetic in the lower classes. Even we will come across this in the polynomials chapter also, division algorithm of polynomials. Euclid's division lemma. Euclid is a famous mathematician. He is known as a great mathematician, and he gave one statement for this Euclid's division lemma, which we use to find HCF of numbers, HCF, highest common factor of numbers, and also we use Euclid's division lemma to study the properties of numbers. Properties of numbers we will discuss in detail. So now come to our lower classes. You see, when we divide 7 with 2, that is 7 divided by 2, 2 3s are 6, 7 minus 6 it is 1. So when we divide 7 with 2, 7 divided by 2, so 7 and 2 are two numbers are given. When we divide 7 with 2, we got two more numbers. One it is 3, the other one is 1. What we call this 3 is, it is quotient, and 1 is known as remainder. 1 is known as remainder. So we have come across this concept in the lower classes. Now we have a relationship between these four numbers 2, 7, 3 and 1. So what we call this 7? This 7 is known as a dividend. 7 is known as dividend, and what we call this 2? This 2 is called a divisor. Divisor we have come across in the lower classes. Divisor, dividend, quotient and remainder we have come across in the lower class, that is dividend is equals to divisor into quotient plus remainder. Divisor into quotient plus remainder. So what is dividend here? It is 7, that is equals to divisor it is 2 into quotient it is 3 plus remainder it is 1. Now multiply, use the Bodmas rule. 2 into 3, 2 3s are 6, 6 plus 1 it is 7. We got 7 is equals to 7, that is LHS is equals to RHS. So there is a relationship between dividend, divisor, quotient and remainder, that is dividend is equals to divisor into quotient plus remainder. What is the relationship between divisor and remainder? It is always the remainder 1. Here we got remainder is 1, that is less than the divisor 2. So we know, we have studied in the lower classes that remainder will be always less than the divisor. So here you should remember that remainder will be less than the divisor. So this formula R will be less than, that is remainder will be less than the divisor. It is divisor. So this concept only we are discussing under Euclid's division lemma. Euclid's division lemma. So what is that Euclid's division lemma? We will discuss in detail. So did you understand this? So dividend is equals to divisor into quotient plus remainder. where remainder will be always less than the divisor. That is, remainder will be always less than the divisor. This concept will study under the name of Euclid's division lemma. Is it clear? Now, Euclid's division lemma states that for given any two positive integers a and b are given positive integers a and b, there exist unique integers q and r. Unique means what it is alone. Only one what it is unique integers q and r satisfying what it satisfies the two integers a is equals to b into q, that is bq plus r, where r is greater than or equals to 0 and less than b. So as we have discussed in the previous, when we divide 7 with 2, when we divide 7 with 2, what we got here it is, so 2 3s are 6, 7 minus 6 it is 1. 1 is the remainder we got. So this can be written in this form, where a is equals to 7, that is equals to b is equals to divisor 2 into q is equals to 3 plus remainder it is 1. Similarly, when we divide what it is 12 with 3, 3 4s are 12, 12 minus 12 it is 0. Therefore 12 can be written as 3 into q it is 4 plus remainder it is 0. So these numbers are written in the form of a is equals to bq plus r, where r is greater than or equal to 0 and less than b. Here r is nothing but a remainder and q is nothing but it is a quotient and remainder, where b is the divisor and a is the dividend. So always remainder will be equal to 0 or more than 0, and it should be less than always the divisor b. We have seen with these examples. Even if you take 15, when we divide 15 with what it is 4, 4 3s are 12, 15 minus 12 it is 3 we got here. So this can be written as 15 is equals to 4 into 3 plus remainder it is 3. So we can write these numbers in the form of Euclid's division lemma, that is a is equals to bq plus r, where the r is greater than or equal to 0 and less than b. So here if you get remainder 0, then 3 is there here. For example, if you take 12, when we divide 12 with 3, we got remainder 0. Then the divisor 3, that is the value of b, is the factor of the number a. B is a factor of the number a, and that is the what it is. B is here is nothing but what it is, divisor. So we use this concept to find HCF of two numbers. We will discuss in detail. So the first application of Euclid's division lemma, it is we can use this Euclid's division lemma to find HCF, that is highest common factor of two numbers. We have studied in the lower classes using different methods like prime factorization method, long division method we studied, and writing the factors of given numbers if they are small numbers, and we identify the highest common factor from the common factors. We use different methods to find the HCF. Now we are going to use Euclid's division lemma to find the HCF of two numbers. So what is Euclid's division lemma? It is given positive integers a and b, there exist unique integers q and r satisfying a is equals to bq plus r, where r is greater than or equal to 0 and less than b. Here r is known as remainder and b is known as divisor, q is known as it is quotient, a is known as what it is here it is a is known as now we will solve this sum using Euclid's division lemma to find the HCF of 135 and 225. What is HCF here? HCF is nothing but highest common factor. As I told you, factors are what? The numbers or the divisors which leave remainder 0. On division are known as factors. So here highest common factor is nothing but HCF. How to find here highest common factor of two numbers 135 and 225 using Euclid's division lemma. What Euclid's division lemma? It says that let a and b are two integers. Let a and b are two integers, and a is greater than b. A is greater than b. Then there exist two numbers q and r such that a is equals to bq plus r. Such that a is equals to bq plus r. So this statement is known as Euclid's division lemma. If remainder is zero, then b is known as what it is? It is HCF of a and b, or b is simply it is a factor of a. So that number itself is a factor for b, is also a factor for b, and b is also a factor for a. Therefore, b is the highest common factor of a and b. Thus, it is possible when remainder is 0. When remainder is 0, we can say b is highest common factor of a and b. Now we are applying this concept to find what the HCF of the two numbers. Here, given two numbers are what? 225 and 135. So a is equals to 225 and b is equals to 135. As I told here, a should be greater than b. A should be greater than b. Then find first here you divide the two numbers. Long division method we are using. So 225 is divided with what? It is 135. 135. So this step here, this is a and it is b. So 135 ones are 135. 135 twos are, it is 270, which is much bigger than 270. Now subtract 5 minus 5, it is 0. 2 minus it is not possible, go for borrowing, then it will become 12. 12 minus 3, it is 9, and here it is, what is there? It is 1. 1 minus 1, it is 0. So now we got remainder, it is 90. So this first step, so a is equals to what? That is what is using Euclid's division lemma. Euclid's division lemma, it says that Euclid's division lemma, it says that by using Euclid's division lemma, what it is? A is equals to bq plus r, where r is greater than or equal to 0 and less than b. Now here a is equals to what? 225, right? That step 225 is equals to b is equals to 135 into q is equals to what it is? 1 plus r is equals to what? It is 90. Since r is not equals to 0, what is r? It is remainder. How much we got remainder? It is 90 and it is not equals to 0. Next we should continue the same step by taking what it is b as what it is? B as the dividend and b as the dividend 135 and the remainder as the divisor. Now this will act as what? B, and this will act as what? A. So 90 ones are 90. So 135 minus 95 minus 0, it is 5. 13 minus 9, it is 45. So now what we got? Remainder, it is 45 and the remainder is not equals to what it is? It is not equals to 0. Therefore, what is the here? It is a, that is 135 is equals to a, b is equals to 90 into quotient, it is equals to, that is q is equals to 1 plus remainder is equals to what again? It is 45. Since again here the remainder is not equals to 0, here remainder it is 45. So again you continue the next step. So for the next step, 45 will act as what? This 45 will act as the b, that is the remainder, and then here the divisor 90 will act as the dividend, which is a. So now we divide with 45. 45 twos are 90. So 90 minus 90, it is 0. Now we got remainder, it is 2. So therefore the next step, it is 90 is equals to 45 into quotient, it is 2 plus remainder is 0. Since remainder is equals to 0, therefore the b value, what is b value here? It is 45. Therefore 45 is the HCF of highest common factor. HCF of what? 225 and 135. 225 and 135. So like this we will find the HCF of 225 and 135. So that long division method, what we did, that only we are writing the steps in the form of A is equals to BQ plus R. Till you get remainder 0, we have to continue those steps. If once remainder get 0, then the B value is nothing but the highest common factor of the given numbers. Is it clear, children? Yes? So one more sum. Use Euclid's division lemma to find the HCF of 867 and 255. Here A is equals to 867 and B is 255. So what is Euclid's division lemma? A and B are two integers, then there exist two integers Q and R such that A is equals to BQ plus R, where R is greater than or equal to 0 and less than B. Now what is HCF of the two numbers A and B? B will be the HCF of A and B when remainder R is equals to 0. Now find where we get R is equals to 0. Till we reach remainder is 0, we need to continue the steps. So the first step is divide 867 with 255. So at what table it will go in the 255 table? It is so 255 into 1 is equals to 255. 255 into 2 is equals to 5 5s are 10. 2 5s are 10 plus 1, it is 11. 2 2s are 4 plus 1, it is 510. Next, 255 into 3 is equals to 3 5s are 15, 1 is there. 3 5s are 15 plus 1, 16. 3 2s are 6 plus 1, 765. It is approximately 3 times it will go. That is 255 into 3, it is 765. Now subtract 7 minus 5, it is 2. 6 minus 6, it is 0. 8 minus 7, it is 1. So we did not get the remainder as 0. Therefore, the first step is A is equals to 867, that is equals to 255 into 3 plus 102. Here this 255 is B and this is A, this is a Q, and here 102 is what it is? R. Now what to do? Now take B as the dividend and remainder 102 as the divisor. Divide 255 with 102. So 102 ones are 102, 102s are 2 2s are 4, 2 zeros are 0, 2 1s are 2. 5 minus 4, it is 1. 5 minus 0, it is 5. 51 we got. Even in the second step also we did not get what it is. The remainder is 0. Therefore, the second step it is 255 is equals to, that is 102 into 2 plus 51. Again here the denominator is, the remainder is not 0. So continue the next step. It is now 51 will act as the divisor and 102 will act as what? Dividend. Now divide. It will go with the 2 table. 2 1s are 2, 2 5s are 10, 102 it is. Now 102 minus 102 is equals to 0. Now we got the remainder 0. Therefore this 51 is known as what? HCF. Therefore it is 102 is equals to 51 into 2 plus 0. Now as we have got 0 as the remainder and this B value 51 is the HCF of given two numbers. Therefore 51 is the HCF of 867 and it is 255. 255. Like this we will find the HCF of two given numbers by using the division algorithm. So 51 is the HCF of 867 and 255, which is when we got 51 at the last step where we got the remainder is 0. Therefore 51 is the HCF of 867 and 255. Is it clear, children? Yes. Now we will discuss one more application of Euclid's division lemma to study the properties of numbers. Now we discuss the second application of Euclid's division lemma. So what is the second application of Euclid's division lemma? We use Euclid's division lemma to study the properties of numbers. So one such problem it is we are going to discuss now. Show that every positive even integer is of the form 2q. So positive integers will be in the form of 2q, and every positive odd integer is in the form of 2q plus 1, where q is some integer. We need to show the positive integers are in the form of 2q and the even integers are in the form of 2q plus 1, where q is some integer. So here, what are first of all positive even integers? Positive even integers. Positive even integers. What are positive even integers? So we know integers are positive integers are what? 1, 2, 3, 4, 5, 6 and so on. In this, even integers are what? 2, 4, 6 are even integers. 2, 4, 6 are even integers. Then what are odd integers? Odd positive integers. It is 1, 3 and 6, 5. 1, 3, 5 are odd integers, whereas 2, 4, 6 are even integers. We need to show 2, 4, 6 in the form of 2q, and it is 1, 3, 5 are in the form of 2q plus 1. See here, 2 can be written as 2 into 1, and 4 can be written as 2 into 2. 6 can be written as 2 into 3. Here if you observe, 2 is the common number. So this can be written as, if you take 1, 2, 3 are integer, some letter called q, then we can write it as 2q, and this as 2q plus, so this is also 2q, and this is also 2q, where q is equals to some integer, where q is equals to 1, 2, 3, that is positive integers. So integers, positive integers, positive even integers like 2, 4, 6 can be written as in the form of 2q, 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 2q. Similarly, odd integers, 1 is there. If you take 1 is equals to what we can write? 2 into 0 plus 1. 2 into 0 plus 1. And 3 can be written as 2 into 1 plus 1. 5 can be written as 2 into 2 plus 1. 2 into 2 plus 1. If you observe here, it is 2, 2, 2 is the common. So this can be written as, if you take 0, 1 and 2 are some integers or some whole numbers, even we can call it as 0, 1, 2, 3 are whole numbers or integers, then we can write this as what? 2q plus 1, and this as 2q plus 1, and this 5 as 2q plus 1, where q is equals to some integer like 0, 1 and 2, 3. Like this numbers, if you see here, this even integers, even positive integers can be written in the form of 2q, and odd positive integers can be written in the form of 2q plus 1. Now we are going to use this Euclid's division lemma, how to write even positive integers in the form of 2q and positive odd integers in the form of 2q plus 1. Let a be any integer, let a be any positive integer, let a be any positive integer, and here if you see here 2q plus 1, when you compare with the Euclid's division lemma, 2 stands for what is bq plus r. Here 2 stands for what is b integer. Let a be any positive integer and b is equals to 2, and b is equals to 2. If b is equals to 2, apply Euclid's division lemma by using Euclid's division lemma, division lemma. So what we can write? What is Euclid's division lemma? It is a is equals to bq plus r, where r is greater than or equals to 0 and less than b. Here b is equals to 2. Here b is equals to 2. Here b is equals to 2. Therefore r will be what it is. Less than 2 means 1 and 0. It should be equals to 0 and more than 0. Equal to 0 means it is r is equals to 0 and r is equals to 1, because r is less than b. B is equals to 2. Less than 2 means it is 1 and 0. So the two possible remainders will be there, 0 and 1. 0 and 1. Now this can be written as a is equals to 2q. If remainder it is 0, if remainder is 0, if r is equals to 0, then if r is equals to 0, then a is equals to b is equals to what it is 2q plus remainder is 0, that is A is equals to what it is? 2q. A is equals to 2q. Then if R is equals to 1, then R is equals to 1, then A is equals to what? 2q plus R. 2q plus R is equals to what it is? 1. R is equals to what it is? 1. Now 2q represents what? Even numbers, and 2q plus 1 will represent what it is? It is odd numbers. Therefore, if R is equals to 0, then A is equals to 2q plus 0, that is A is equals to 2q. What this 2q represents? It is an even number. 2q represents even number. And if R is equals to 1, then A is equals to 2q plus R. In the place of R, I am writing as what? 1. So these numbers, it represents what it is? An odd number. Now here the remainder is 0. So and divisor it is 2. When we divide any number with 2, if remainder is 0, we call those numbers are even numbers. And when we divide with 2, if remainder is 1, we call those numbers are odd numbers. So now what we can conclude from this? We can conclude therefore every positive even integer, every positive even integer is of the form 2q, and every odd positive integer is of the form 2q plus 1. So like this we can prove this statement, we can show this statement. As we know, when we divide any number with 2, if it leaves remainder 0, we call those numbers are even numbers, and if they leaves remainder 1, we call those numbers are odd numbers. So we can say that every positive even integer is of the form 2q, and every odd positive integer is of the form 2q plus 1. Is it clear, children? Now one more similar problem from exercise number 1.2, the second bit. Show that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5, where q is some integer. We have to show any positive integer is in the form of 6q plus 1, 6q plus 3 or 6q plus 5, where q is some integer. Here the 6 represents what? B, that is a divisor, and plus 1 plus 3 plus 5 what they represent? By using this, by comparing with the Euclid's division lemma, 1, 3, 5 represents what? The remainders or values. Now here consider, let A be any positive odd integer. Let A be any integer. Let A be any positive, you can write any positive integer, and B is equals to what? Here it is 6. B is equals to, here it is 6. By using Euclid's division lemma, that is EDL, by using Euclid's division lemma, what we can write? A is equals to 6q plus R, where R is greater than or equal to 0 and less than B. Here B is equals to what it is? 6. Where R is greater than or equal to 0 and less than equals to 6. Therefore, R can take the values as 0, 1, 2, 3, 4 and 5. So remainders may be either 0 or 1 or 2 or 3 or 4 or 5. Now check for each case. If R is equals to 0, then A is equals to what? 6q plus 0, that is equals to 6q. 6 is equals to what we can write? 6 as 2 into 3 we can write, that is 2 into 3q. Again we are multiplying 3q with 2. So what we call those numbers? Even numbers, and here the remainder is 0. Therefore this is an even number. Therefore, here A is equals to 6q we got, and this is even number. If R is equals to 1, if R is equals to 1, then A is equals to 6q plus 1, 6q plus 1. Now here the remainder is 1. Here we got the remainder is 1. Therefore, what we call these numbers are what it is? Odd numbers. Similarly, if you take if R is equals to 2, then R is equals to 2, then A is equals to what it is? 6q plus 2. 6q plus 2. R is equals to A is equals to 6q plus 2 here. So what we can write this 6q plus 2 again it is can we take here what it is again here we got 2 is the number we got so when we divide 2 with 2 we get remainder is 0, therefore the remainder will be here, it will be 0, and again this number will be again what it is even number, or simply it is as we have proved that 6q is an even number, and when we are adding here 2 is an even number or not. So sum of two even numbers is also an even number. Therefore 6q plus 2 is an even number. The fourth case, if R is equals to 3, if R is equals to 3, then A is equals to 6q plus 3. A is equals to 6q plus 3. So R is equals to 3. 3 again it is an odd number. We are adding an odd number to an even number. So that is 1 plus 3. 1 is 2 plus 3. 2 is an even number. 2 is an even number, and we are adding to that even number 3, an odd number. 2 plus 3, 5. We will get what it is? 5. 5 it is an odd number. Or you take 10 is an even number and 5 odd number, we get 15. That is sum of an even number and one odd number will give you always odd number. Therefore, this is also an odd number. It is also an odd number. Next, if R is equals to 4, then if R is equals to 4, then A is equals to what it is? 6q plus 4. 6q plus 4. Again, 6q is an even number and 4 is an even number. Adding even number and even number, we get again even number. Even number. Next, we'll check for if R is equals to 5, what we get here. If you see here, 6q plus 1. 6q plus 1, we got odd number. When remainder, it is an odd number, so odd number we got, and here 6q plus 3 we got again one odd number we got. Next we have to prove if R is equals to if R is equals to 5, then if R is equals to 5, then A is equals to 6q plus 5. 6q plus 5. So again 6q is an even number. We are adding an odd number to an even number. We get what? An odd number only. Therefore A is equal to 6q plus 5. That is an odd number. That is an odd number. So in this case also we got so odd numbers. So odd numbers are in the form of what? Odd numbers are in the form of 6q plus 1 and 6q plus 3, or it is 6q plus 5. So what we need to prove? Show that any positive odd integer is of the form 6q plus 1, that is odd number 6q plus 1, 6q plus 3 odd number, 6q plus 5 it is an odd number. Odd number. Therefore what we can write the concluding statement, it is therefore any positive integer, positive odd integer is of the form odd. Integer is of the form it is 6q plus 1 or 6q plus 3 or it is 6q plus 5. Like this we can show that every positive odd integer is of the form 6q plus 1, 6q plus 3, 6q plus 5 by using the concept of Euclid's division lemma. I think you understand this today's class. Is it clear, children? And now if we come to the homework part, here I write the homework it is for today's homework exercise 1.1 question number 1, in that second bit is there, and question number 3, question number 4, question number 5. So this is your homework. So today's homework is exercise number 1.1, question number 2, question number 3, question number 4 and question number 5. Thank you, children. I hope you understand. Once again, thank you very much.